The squeeze theorem is especially useful for evaluating certain kinds of limits, such as this one here. The limit as x goes to 0 of x squared times sine 1 over x. This theorem is also known as the Sandwich Theorem in some circles. So let's take a look at what's happening with this function as x goes to 0. X squared is fine. That's a very well-behaved function. We know what's happening there. It's this sine of 1 over x that's extremely poorly behaved as we go in towards x equals 0. Right? We divide by something smaller and smaller and smaller, so this bit inside the parentheses is getting larger and larger and larger. It's oscillating ever more frequently. In fact, let's look at what just sine of 1 over x by itself looks like, just to see how poorly behaved this function is and why it's hard to deal with it. Okay, it looks something like this, and you can see as we get in closer and closer to 0, it just goes haywire on us, and it's really hard to say what's happening at all, right? It almost looks like it's just completely filled in there. And so that's certainly not the kind of thing we want to wade into. Note that this function here is only sine 1 over x. We haven't added in the x squared yet. So now let's look at what happens when we multiply this thing by x squared and then graph that new function. Okay, so here's x squared sine 1 over x. And we can see that it's still going a little bit haywire here in the middle, but you can also note that it's being pulled down. The function value itself is being pulled down to 0 as x approaches 0, right? Notice here, up here we're already at 0.1, and we're only down to negative 0.1 down here. So this is really coming in right to 0. So graphically, we can see that this limit is essentially going to equal 0 here. But how can we justify that analytically? Well, this is where the squeeze theorem comes in. Okay, the squeeze theorem says that assume the functions f, g, and h satisfy f of x less than or equal to g of x less than or equal to h of x for all values of x near a except possibly at a. Then, if the limit as x goes to a of f of x equals the limit as x goes to a of h of x equals L, then the limit as x goes to a of g of x equals L. Okay, let's break this down a little bit. What's happening in this theorem, and why it's called the squeeze theorem or the sandwich theorem, is that this function g of x is trapped. Okay, it's trapped between two other functions, f of x and h of x. So g of x is trapped in the middle of f of x and h of x. It works really well when you have a somewhat ill-behaved function such as sine 1 over x that's bounded. So how is this sine 1 over x bounded? What do I mean by that? Well, the thing with sine of anything is we know that it is a maximum. The maximum all this sine 1 over x business can be, right? The maximum it could ever be is 1, right? Because sine of anything, the biggest it ever gets is 1. And similarly, what do you think the minimum is? Well, the min of anything, sine of anything, right, is negative 1. So sine of 1 over x can oscillate as wildly as it wants. It is trapped between 1 and negative 1. And that holds for sine of anything, that holds for cos of anything. So the squeeze theorem is especially useful when you have sine of something and cos of something times some other well-behaved function. So now let's look at our function in its entirety. Let's look at all of this x squared sine 1 over x. Well, we can trap that function then between positive x squared and negative x squared. So let's see, let's write this as negative x squared less than or equal to x squared sine 1 over x, which is less than or equal to positive x squared. That is legit because sine 1 over x, no matter what it does, the biggest it gets is 1. That puts us over here at x squared. The smallest it gets is negative 1. That puts us down here at negative x squared. In fact, let's graph these three functions together to get a visual feel for what this looks like. Okay, so now we can see what's going on a little bit better. We have this top function, which is x squared. The bottom function, this green one, so the blue one is x squared. The green one is negative x squared. And then the middle one is our function. This red one is x squared sine 1 over x. And you can see it's trapped, or shall we say squeezed, between positive x squared and negative x squared. Okay, so back to our theorem. We have f of x less than or equal to g of x less than or equal to h of x. Well, in our case, our negative x squared is our f of x. Our positive x squared is our h of x. And the one trapped between them is x squared sine 1 over x. That's our g of x. Now, is it true that the limit as x goes to 0 of negative x squared equals the limit as x goes to 0 of positive x squared equals some limit L? Well, yes, that's true, because both those limits equal 0. Those are polynomials, so we can simply plug in 0 for x, and we get 0 for both of them. Well, since g of x, our main function, is trapped in between those, we conclude, therefore, the limit as x goes to 0 of x squared sine 1 over x must also equal 0 by the Squeeze theorem. Indeed, that's the conclusion of the Squeeze theorem. It tells us the one sandwiched in between them also goes to that same L. In our case, L is 0, so our limit does indeed equal 0. So it's a fairly elegant theorem and very useful for certain kinds of exercises in calculus. So I recommend spending some time with this theorem, getting to know it, and getting to recognize what kinds of exercises it could be useful for. Because if you recognize when this theorem needs to be used, it's so fast and it's a very elegant solution and a great way to rack up some points. If you miss that we need the Squeeze theorem, you can spend a lot of time driving yourself crazy trying to find limits that are going to be impossible without this theorem. So know it, know when to use it, know how to use it, and be able to use it quickly.